Welcome back to geometry. As a reminder, we do have the distance formula, and we can use the distance formula when we have whole numbers, and we can deal with fractions. We're not going to be allowed to convert these to decimals right away because we have a third here. So when we set these up, I like you to use the fill-in-the-blank form of the equation. The x's, x and y for one point, and the x and y for the other point. I notice when I simplify these, I'm going to get 8 squared plus 0 squared. And 8 squared is 64, the square root of which is 8. So the distance from my first point here is 8. Distance is positive. I don't need to deal with the positive and negative. When I am dealing with fractions, my first set of fractions is going to simplify to 4 over 2. That's going to be 2, which needs to be squared. My second set of fractions, I am going to have to multiply them in order to get the same denominator so that I can add or subtract them. I end up getting sixths in the denominator. This becomes negative 9 minus 4, which is negative 13, and that will need to be squared. Anytime I square a positive, I get a positive. When I square a negative, negative times negative is positive. 69 divided by 36. And when I simplify that, I get 18 and 7/9. And I'm going to take the square root of that. And I'm going to get 4 and 3/9. So that would be my final answer for the overall distance. Okay, so we need to be able to classify solids, describe the different types of cross sections that we can get, and describe what are called solids of revolution.
In our 3D shapes, we have a variety of different kinds of prisms. We have a cube, a rectangular prism, and a triangular prism here. If instead of having 2 parallel bases, we have one base that comes up to a point, which is called a vertex. All points in 3D shapes are called vertices. Here's a pyramid that's triangular, and a, whoops, don't do that, and a pyramid over here that's square. So these are 2 different types of pyramids. Our next one we have is a cylinder, and there's a relationship between the cylinder with 2 parallel parts and a cone that comes up to a vertex. And last we have a sphere. Now there are many other unusual shapes, but these are our biggies.
So we're looking for solid polyhedrons, and on these ones, the first one is going to be a polyhedron because all sides are flat. And we would typically call this a rectangular prism. In our second shape, are all of the sides flat? Yes, it is a polyhedron, and this has a base that has 6 sides, so it is a hexagonal pyramid. Anything that has a curved side is not a polyhedron, but it does have a name. It's called a cone. Okay, again, this is a polyhedron because all sides are flat. It is a square pyramid. This is not a polyhedron. I would probably call this a half or semi-cylinder. Half a cylinder. The 2 sides that are parallel are the triangles, so this is a polyhedron, and it is a triangular. formalism.
Anytime we look at these 3D shapes, we have, these are all called polyhedrons because all of the sides are polygons. There's no weirdo curves on anything. And the flat part that looks like a polygon is a face. Every corner, here, and here, and here, and here, are called vertices or vertex. That's our name for corners. And the edge is the fold where two faces meet and form a segment. Now there is such a thing as non-polyhedrons, and they're not going to have a lot of these parts. We do have a cone that does have a vertex, but you notice that it doesn't really have edges. Might have a face, the base, but the other faces are not necessarily flat, so we wouldn't call them faces. So not all 3D shapes are polyhedrons. There are 5 regular polyhedrons. Regular, meaning that all of the sides are equal, regular polygons. In both the tetrahedron, the octahedron, and the icosahedron, all of the sides are triangular. This has 4 sides, this has 8, and this has 20. Then we have the cube you guys are very familiar with. And in the dodecahedron, like my hall pass, we have 12 sides, and all of the sides are pentagons. They do get to be pretty strange and unique. They're actually kind of fun to look at. One that you guys have seen many times is, looks like a soccer ball, doesn't it? Soccer balls are made up of hexagons surrounding pentagons. Here's the hexagons here, and the blacks are all pentagons, and that's called a buckyball. In all polyhedrons, there's a relationship between the faces, the edges, and the vertices. This is Euler's law. And when it's a 3D shape, we have one formula here. And when we actually look at the net, the formula will change very slightly. It will go from +2 to +1. Let's see how these work on these two shapes over here. We have a hexagonal prism, and we have the net of an octahedron. So we're going to start by looking at the faces. And in this first shape, there's 8. There's actually 8 faces in both of these. Here I'm counting all the sides. Here I'm counting all of the separate shapes. Then we're going to look at the vertices. And the vertices on this one, if I count the full thing, there's 6 up on top here and 6 down below for a total of 12. And I have them marked down here. There are 10 vertices on this net. There will actually be more vertices on the net than there will on the 3D shape, because I've got to show this spot even though it will connect with this spot. Then we have our edges, and the edges are the flat spots here, and there are 6 around the bottom here. Then there's another 6 that look like this guy here, and then there's 6 across the top. So that's a total of 18. And as you see, the formula works. Down here, we're going to count up all of the lines that it takes to make this, not including the tabs, of course, and we end up with a total of 17. So once again, the formula works. Both of these are examples of Euler's formula, one for the actual 3D shape and one when you're looking at the net. Make sure you know which one you're using. We want to take a look at is what are called cross sections. We have a slice across a cone. When we open that up, we would actually get a circle the way that they've sliced it here. But not all cross sections have to be parallel like these ones are shown. They can be strange angles if you want them to. Here's a cube, and you notice that I ended up with a hexagon because of the way that I sliced it. It's actually going through quite a few different edges here. If you want to take a look at some other ways that you can cross things, we'll go to this. You notice here that we have a cube. We can take a look at different shapes here, tetrahedron, octahedron, and give you some examples. So here I have an example of a cube, and I can show you some different. There's a pentagon. It's another pentagon. Pentagon still. Pentagon still. There's a way to get a hexagon in here as well. Let me see if I can get it to do it.
So we should be able to name these based on what type of sides they have. Do they have two sets that are parallel or not? Another thing that we can do when we're looking at solids is we can slice them. And when we slice them in specific directions, we think about what would the shape of that slice look like. Now we can get really strange when we slice these, but in general, we're going to have it, if it's parallel to a side, this one is going to have a hexagon as the slice. In a triangular pyramid, when we slice that, it's going to be a triangle. Think about when we slice this. There is no rectangle on here, but when we slice it, it's going to be a rectangle. Both of our next two shapes, when we slice them, we will get a circle. That circle can come off of a cone or in any direction off of a sphere. If you look very, very closely at my last problem, it's starting to tip the side. I do still have two parallel sides and two that are not, so this one was going to have a trapezoid. They can get some strange shapes because we don't have to cut them parallel to a side. The last thing we take a look at doing is think about this line here. Think about this line here. And what we're going to do is spin it. And when we spin it, this shape is going to move all the way around, and it's going to end up creating a cylinder. And if you think about that cylinder, the side is going to still be 9, but the circle on the bottom will have a radius of 4. And we could sketch that out. So if we want to sketch that, we would end up coming up with basically we want two ovals that are close to the same size and the lines connecting those, because the thing that spins goes through this spot right here. If we spin this one on this triangle, this here, we're going to end up with a triangle that spins around, and the base of that is going to end up being a circle, so that one is going to end up being a cone. And if we think about that, the dimensions of that cone are going to be the base has a radius of 4, and the height is 5. That looks like it's going off the edge of my screen. So those are the 3 things that you're going to take a look at today. And your homework will be posted to Google Classroom. Have a good day.